Hi, I'm Marius, and I'm excited to present SEED4D. SEED4D is a synthetic ego-exocentric dynamic 4D project, which includes an open-source data generator, two driving datasets, and a suite of benchmarks. This project is joint work with Theo, Sebastian, Dylan, Elder, Avas, and Thomas. A significant challenge for developing bird's-eye view applications is the lack of automotive ego-exocentric view data. Such data could also help to evaluate the performance of view generalization methods. Existing automotive data, while available in large quantity, are predominantly egocentric and outward-facing, limiting their utility for testing multi-view methods. Most 3D datasets contain numerous viewpoints, but usually only consist of exocentric views and are not driving specific. Acquiring large amounts of real-world ego and exocentric views, for example with drones, would be costly and very time-consuming. This gap highlights the need for synthetic data. We introduce a customizable and user-friendly data generator. Our data generator leverages Scala, an open-source, high-fidelity simulation environment, for generating rich, annotated, synthetic, ego and exocentric view data. The data generator allows to flexibly adjust the number of views, the number of vehicles in the surrounding, the camera placement both on the vehicle and in the surrounding of the vehicle. This way, it enables efficient capture of ego and exocentric viewpoints in static and dynamic environments. The left part here shows an example camera placement, whereby green indicates the exocentric views and blue the egocentric views. The ego vehicle itself here is invisible. The right part shows a semantic segmentation of the scene. Our code generator includes egocentric camera configurations that replicate the camera setup used in popular datasets such as nuScenes and Waymo. The image here highlights the camera configurations as it can be found in nuScenes and Waymo, and the respective camera configuration within the data generator. All files are outputted in a Nerve Studio compatible format, ensuring seamless integration into common 3D or 4D training pipelines. We use our data generator to create two large-scale datasets: a static dataset comprising egocentric and exocentric views captured in static stationary scenes. This dataset is best suited for testing ego to exocentric view generalization. The dynamic dataset consists of multi-temporal sequences with synchronized ego and exocentric viewpoints. Let's examine each dataset in detail. The static ego-exo dataset consists of around 2000 scenes. Ego views have a size of 1600 by 928 and exo views of 800 by 600. All egocentric cameras follow the nuScenes camera configuration shown before. On the right, we can see a number of example views. The top row shows 2 times 6 ego views. The bottom row shows 2 times the corresponding exo views. In total, we collect 7 ego views and 100 exo views per scene. The dynamic ego-exo dataset comprises 10,500 trajectories from around 500 scenes, with an average of 21 vehicles per scene simultaneously collecting data. Each trajectory consists of 100 time points. To maintain a manageable dataset size, both egocentric and exocentric views are collected with a smaller size than in the static dataset. On the left, we can again see a number of example views, now from different time points of the same scene. The two top rows show ego views. The three bottom rows show corresponding exo views. The availability of well-annotated ego-exo data allows a number of diverse applications. One of them is view image to 3D generalization, whereby egocentric views are inputted into the model and the model is trained to reconstruct exocentric views. This task is a generalization of bird's-eye view prediction. The metric depth annotations can also be used for testing monocular depth estimation methods. The unique combination of dynamic ego-exo data also allows to evaluate 4D prediction methods. With our benchmarks, we tested multi-view novel view synthesis, monocular depth estimation, and single-shot multi-view synthesis. Our first benchmark trains per-scene optimization methods on inward-facing views. All models are trained on 80 exocentric views and evaluated on the remaining 20 exocentric views. We evaluate splat factor, nerve factor, and K-planes. We find that K-planes generalizes best towards the novel views. This is also supported by the qualitative results, where K-plane images look sharp and are not blurred by artifacts. The first image per row is always the original reconstruction, and the second view is the zoomed-in version. We here show again RGB, splat factor, nerve factor, and K-planes. We test the performance of two metric monocular depth estimation methods, namely Zoe depth and metric 3D, on the exocentric view data. We find that metric 3D performs significantly better in our benchmark. For the view image to 3D benchmark, we evaluate three categories of models. Two metric depth models evaluated by pixel-wise depth projection. Three iterative per-scene optimization methods. And three feed-forward single-shot parameterization method that learn priors across the scene. We find that monocular depth estimation models, which only use projected pixel information, result in low-quality novel views. The novel views contain large, unfilled textureless parts. Per-scene reconstruction models perform slightly better, but they suffer from the little view overlap in the egocentric data. Feed-forward methods perform reasonably well. Their learned priors across multiple scenes allow them to generalize toward unobserved scene parts. However, no model performs optimal on this benchmark. SEED4D opens up a number of interesting future research directions. Since the Exo Camera Setup closely models the nuScenes camera, performing zero-shot sim-to-real transfer would be interesting. Prior work has shown that existing monocular depth estimation methods profit from training on synthetic data. Maybe this is similar for view image to 3D methods. Here, style transfer methods could help to close the domain gap between synthetic and real-world data. 4D prediction is currently still in its infancy, potentially due to the lack of large datasets. Here, our datasets could help. Our datasets could also be used for generalizability testing of 4D reconstruction methods. You can visit our project page for more information, or you can directly clone the data generator and generate data yourself.